So Otto Hahn and is it Fritz Strassmann, okay, discovered using neutrons and the heavier elements that you can actually make certain elements split in half. You can split uranium in half. Fermi, by the way, Enrico Fermi, who was an Italian scientist and now is in America, right, discovers really that the way to do nuclear reactions is to use neutrons. Okay, positively charged things are hard to get into a nucleus because they have to be going fast enough, and that's because the nucleus will repel anything that's positive. A neutron can just wander into the nucleus. In fact, a paradoxical thing is that we have to actually slow the neutron down because fast neutrons can actually just go right through this neutron. If they're going too fast, they'll go through the nucleus and they won't cause a nuclear reaction, right? So basically they have to go slow enough that they stick to the nucleus, right? Once they do that, the nucleus will become dyspeptic because uranium-236 is not stable, right? And it will split. It'll do this little thing. It's kind of like a lava lamp, right? They'll split and then they'll shoot off. There'll be some extra neutrons that are orphaned. And the reason for this is that lighter nuclides don't require as many neutrons to bind, right? Whereas this needs a lot of neutrons. These don't need as many. So these guys are kind of orphaned in the process, okay? Now, they discovered that this reaction releases, this particular reaction is something like 173, we're going to do it in a second here, 173.3 million electron volts, right? Let's just think about this. Up until that time, they had stuff like dynamite and TNT and stuff like that, right? Okay, that releases on the order of 10 electron volts per molecule, 20, 30, maybe 100 if it's really zippy. I mean, I just don't know, okay? But something small like that, right? This per atom is releasing this much, right? That's a lot more. This is if you could make a bomb, if these could set off more uranium atoms, you could set off a chain reaction. If you could have a critical mass, right? You could set off a much bigger bomb. This bomb would potentially be a whole lot bigger than a conventional bomb. Okay, so this is the difference between what chemical reactions and nuclear reactions, right? The strong nuclear force is a much stronger force, and therefore the potentials in nuclear physics are much bigger. Okay, so let's look at one of these problems. We have to be able to solve a problem. Now, this is just a nuclear reaction. It's solved exactly the same way that we solve the other nuclear reactions, except there's one twist, and that is that they'll say that uranium plus a neutron creates barium and is this krypton, right? Plus some neutrons, right? So we've got to figure out how many neutrons, and that's pretty simple. This is balancing the equation. So this is, remember, this is a 1, 0, right? So 235 plus 1, there's 236 mass numbers here, right? So this has to add up to 236. So we've got 141 plus, and this is going to be some number here, right? So 141 plus 92 is 233, right? Okay. So 233 plus, well, how many neutrons? Well, 236 equals 233 plus 3 neutrons. So the answer here is 3 neutrons, just like the picture showed, right? To be sure, I've found fission reactions where it's 4 or 5 or 6, so you got to figure it out, right? So again, that math is just add up the top numbers here. A neutron is a 1, 0, right? And then this is going to be 3 times 1, 0, right? So 233 plus 3 is 236. 235 plus 1 is 236. It's balanced, okay? Equals 236. Okay, so what is the Q value? Well, the left side of this is 1, and you have to look up the mass of a neutron, right? So 1.008665 plus, and then uranium-235, you'll have to look up that, right? So 235, and you'll have a little reference to look that up in, 43923. And then that turns into, and then look up the barium-141, right, which is 140.914406 plus, and then the krypton-92 is 91.926153. And then don't forget your neutrons, right? So plus 3 times 1.008665, right? So you put all these things, you put all their masses down there, and now we're going to type these into the calculator, right? And basically we're going to go left side minus right side, okay? If we lose mass, then that mass, of course, is energy, right? So let's find the mass defect here. 1.008665 plus 235.043923. 043 is that. So I get the left side is 236.052588. Let me just double check that. And 043.923. Yes. Okay, that's good. All right. And now I'm going to do the right side. So 140.914406 plus 91.926153. 926153 plus 3. Don't forget the 3 neutrons, right? 3 times 1.008665. And on the right side, I've got 235. That's a huge mass defect, 0.866554, right? So left side minus right side times 931.5 is how much? Okay, so I can do this. Let me just double check this. Okay, 141.914406. I'm just double checking. So 926153. There we go. I'm not very good at these because I get in a hurry. Okay, so now I'm set. I can go left side minus right side. The mass defect is 0.186034. 0.186034. And I'm going to multiply by 931. Because you just multiply by 931. That's because this is how many atomic mass units we've lost. And if you multiply by that, this is the energy equivalent of that. Right, so that's MeV per U. Whoops, U. There we go. So multiply by 931.5. And I get 173.3. Okay. Okay. How many sig figs do I have? Well, this number here, all of those digits are significant. So this has 6. This one only has 4, though, so we have to round it to 4. Okay. If we had this to a greater precision, we could write this down with up to 6 digits of precision. Okay. So that is our energy, right? Energy released. And then what is the energy density in joules per kilogram, right? Well, that's per molecule, right? So let's figure out how many moles we've got. A kilogram is 1,000 grams, right? And then divide that by the mass of uranium-235, assuming it's pure uranium-235, right? That'd be hard to do, but let's just go with it. 0.043923. This is grams per mole, right? So 1,000 divided by 235.043923. Obviously, all that precision is not needed. So that is only 4.254 moles. Okay, so now we're going to multiply by 6.02 times 10 to the 23rd. This will give us number of atoms. So times 6.02 E23. So this is actually 1,000 grams of uranium is 2.561 times 10 to the 24th atoms, right? And then every atom is 173.3 MeV. So 173.3 times 10 to the 6th electron volts, right? So times that times 1e6. And now we've got electron volts. It's a lot of electron volts. Okay, so that is equal to 4.4384 roughly times 10 to the 32. That's electron volts, right? So let's multiply by 1.602 times 10 to the minus 19th. This is what, joules per electron volt? Okay, so times 1.602. We'll get the answer eventually. E to the minus 19. And this is 7.112. Huh? I just got 7.11 times 10 to the 13th. and that is joules per kilogram, right? And if I divide that by 6, it's 7 times 10 to the 7th megajoules per kilogram. So energy densities typically are in megajoules per kilogram. So I, again, just subtract 6 from that, and we get 7.11 times 10 to the 7th megajoules per kilogram. So that's pretty good. That's a pretty good energy density, right? Which brings up, of course, this XKCD cartoon, right? Here are energy densities of common fuels: sugar, right? Coal is a little better. Fat's even better, right? Gasoline, oh, that's pretty good, right? Uranium, though, is fairly good, right? Why do they have that much, though? 76,000. I don't know. We're off a little bit. You and I are off a little bit. I don't know why. But that's, there we go. That's pretty good. Yeah? I like this joke.